So open the input from the by hand optimization, and then we only change the calculation type. So instead of a one-shot calculation that is a consistent field, we put here relax. Right. The other point that is important to keep an eye on is the number of ionic steps. That is the amount, right? So we compute the density of these two atoms. With the density, we compute the forces, and then we shift the position of the atoms according to the forces in small steps. If we need a lot of steps, our calculation may not finish in 50 steps. And 50 steps is given here with n step. So to be sure, you can put a fairly large value here, right? We have a very simple system, the hydrogen molecule. We will not need 5,000 steps. But you know, to be sure that we actually see the end of the calculation. So these steps are called ionic steps because we are moving the core of our atoms. We optimize the density, that is where we work with the electrons, and when we're done with that, we start computing the forces on the nuclei and then moving them, right? So that is after we have computed the properties of the electrons. And then we said we put a quite large distance between the atoms. If the distance is too large, now 10-10, then the two atoms don't see each other, right? They don't talk to each other, they don't have a bond. But we need a little bit of interaction to get started with the calculation. Right? So there need to be a little bit of attraction that they start moving towards each other. A bit like when you play with magnets, right? If your magnets are too far away, nothing happens. But if you bring them closer and closer, suddenly they snap, right? Similar we do here. So let's say 2.3 angstrom. If you want to be a bit more safe, put 2 there. For lithium, I don't know. You would look at your curve, right? 3.5, and then you can see if things happen. So and then I save that one. A quick look again, right? So that one is important. Calculation relax. The number of steps sufficiently large. And then it should work. So let's try that. So the output I write now in optimize.log. By the way, so when we put relax there as an option, we do not change the size or shape of the unit cell. We only change the position of the atoms. Good. So let's try that and put that in the background. It didn't work. Let's see what's going wrong. So if things go wrong, first thing I normally do is I just look at the total. Right, so now we encounter something that you may not expect. So here it's written that line in name list ions. So it's indicating with the end symbol. Then we open our input again. I use no win, it's a bit faster. And then we look for ions, and we don't have an ions line. The thing is, when we put here the calculation relax, Quantum Expressor wants to compute something about the ions or cores of the atoms. And it expects from us to have a block called ions. But we don't need to put there anything for now. So we just give it an empty block. Okay? And please, I think at that here it matters where you put your block. So put it after electrons and before cell parameters, to be sure. So I save that with colon and W, and then I close the file. You all have added the ions block, yes? Okay.
Professor, if I'm using lithium, do I have to increase the number of bands?
So lithium has 3 electrons in total, right? And it has one valence electrons and 2 in the core. So depending on the potential, you need between 3, 6, 3. How many bands did you put? 5?
5.
It should be sufficient. But yeah, it should be sufficient. There is sometimes the rule that you divide the number of electrons in your system by 2 plus 8. That is a good approximation, because during the optimization it can happen that the electrons don't want to be like in pairs of one orbital. So they're stuck up like that. So you need to include always a bit more empty states to help the convergence. So let's try again. Oh, now it's running, okay? So what I do now is I cancel the calculation with Control C. I redirect the output in optimize.log. I put the calculation in the background, and then I tail the progress of the optimization. And what you will see is it starts with the SCF cycle, first iteration, now the second iteration, until the difference between consecutively computed total energies reaches the convergence threshold of 1 times 10 to the power of minus 6 Rhythmic. So then it tells you somewhere convergence is reached. It gives you new atomic position. Remember, I started with a distance of 2.3 or 2.5, and that was already a bit different. Starts the next self-consistent cycle after the ions have been shifted. It optimizes the electronic density, tries to reach convergence, right? And the distance has shifted again. I have now 2.2 here, and the other position was 0.08. So that will take a time, right? Because I put the two atoms quite far away from their optimal position. So they start slowly moving towards each other. Things are happening. Good. So now I cancel the tailing of that file with Control C, and I want to, the calculation has not yet finished, but I already can open the output in xcrisDen. So I type xcrisDen, 2 times minus, and then PW output, because I want to read my output of the calculation, and I put the optimized.log as argument. See if it's working. And it is over here. So Quantum Expresso then asked me, do you want to display the last coordinates or all coordinates? Because I want to look at the optimization, I choose all coordinates. Continue. And I already have 6 iterations that I can zoom in here. Right, so you see the 2 atoms. If you don't see them, we can change that like that, right, a bit bigger. And then we can go through the 6 iterations, and you see the atoms are moving towards each other. Good. But now I told you I want to show you how to look at forces. Let's see. We go to the Display tab. It's difficult to read when I write here. And then you find forces. F. So look at that. So there you see now 2 arrows that are pretty big. And they become bigger and bigger. Why do they become bigger and bigger? Well, remember the potential we just draw. You know that the force is the gradient of the energy, right? So the steeper the curve is, the larger get the forces. And we are moving at the moment down, right? So my potential looked like that. and we said start here, right? You're moving this direction because you saw the atomic positions go closer. Then we are like a gradient here towards a gradient here. So our forces become bigger and bigger, so they move faster and faster towards each other. Until they reach maybe this point, and then it becomes small again, and at the minimum, the gradient is 0. That is where we have optimized our structure. Are you familiar with the gradient and the potential? Right, if you, okay, now it's actually difficult to see which force is pointing which direction, because they're like so large and they cross each other. If you want to rescale basically the size of the forces, there's an option 2. You go to force settings, and then you change this value, you update, and you will see now the forces are much smaller, right? Maybe we zoom in a bit. It's still too big. Update, too small. 10, 5, almost 7. Right, so now you see little forces, little arrows pointing towards each other, meaning the two atoms are attracted towards each other. Right, we are going to form a bond.